Okay. Hello. Before we get started, I just want to say a couple of things. First of all, we had a really great poster session yesterday. Thank you to all the students who gave posters yesterday. The discussions were great. Students wouldn't stop talking. We literally could not get them to leave.
Yeah.
So I hope this afternoon is going to be just as good, if not better. I hope everyone will attend the posters this afternoon. Other thing I wanted to say was, as we mentioned, NSF is supporting this workshop, and as part of that, we have a survey that we would like everyone to fill out, just about what you came away with from this workshop, how it was good, how it could be better. Yes, you'll get an email about that hopefully soon, and then please everyone fill that out as soon as you can. Okay, so it's my great pleasure to introduce our keynote speaker today, Todd Coleman from Stanford, who needs no further introduction. Please take it away. Thank you so much.
And a lot of folks got a lot of old friends here I haven't seen in a while, so I thought the first thing I do is I'll show you how things have changed, perhaps since the last time I've seen you. So on the left is my son Camden, he's 6 years old, and on the right is my daughter Lila, she's 20 months old. Yes. So with that, I thought I would do is kind of tell you guys the path that I took towards thinking about the math problem that we're going with. And where I started is when I was an assistant professor at the University of Illinois, and I had done a postdoc in neuroscience. So I was interested in playing around with some type of application that involved neuroscience and some fun engineering. And I stumbled upon the way, this is around like 2006, the way people were thinking about brain-computer interfaces, where you instrument someone with a shower cap, EEG, recording brain waves, and people were trying to do very basic things like control the system to move a cursor to the left or to move a cursor on the right. And the essence of how they thought about the problem statistically is imagining that as a binary signal, imagine left or imagine right. We record these waveforms, the EEG, and I basically just update a posterior distribution about this. And, I decode it and maybe move to the left or the right. So a little bit about the basics of how this works is you can imagine that the measurement of the EEG, it's a signal Y, and there's some matrix A, which basically maps the dipoles, which are the little yellow things that you see, and maps them to the actual recordings that you observe. And obviously there's measurement noise. And if we think about some of the basic physiology, we know, for instance, related to movement and a certain frequency band called the beta band, there are these cortical rhythms, right? And so you can take a look at these underlying rhythms. And one of the things that we know quite well is that when you imagine squeezing your left hand versus when you imagine squeezing the right hand, the spatial patterns associated where the voltages are large in magnitude versus small, they change because of there's a sematotopic representation of our brain when we try to imagine doing something to the left versus something to the right. So if you have this spatial information, you can imagine, without going into a lot of details, how you might be able to build a measurement model, and then from which do basic types of Bayesian inference. So this was the essence of how everyone was thinking about this problem. Was basically it's binary signal. We take advantage of the sematotopic mapping in the brain, and then we basically just update a posterior distribution, and then you move the cursor to the left or the right on the screen. But the epiphany that we had is that there's something about this that didn't feel right, because the way brain-computer interface maybe really should work is this interconnection between the human and the computer, and it should be bidirectional in nature as compared to just this one-shot open loop. You imagine something and we decode. And the analogy I like to give is I remember when I was in high school, the first car I got was a 1983 Honda Accord, and I had an alignment problem. And what was interesting is, despite the fact there was an alignment problem, I could still drive the car, because if you let it go straight, it starts to veer to the left. But I see it's veering to the left, and I provide corrective feedback, and yet I can still drive the car despite that. So the high level idea that came to my mind is that where is this notion of feedback, and where is this sequential notion of operation of this device as compared to a sequence of open loop types of control paradigms? So what we got interested in formulating was something that involved a little bit of ideas from maybe control theory, but there's posterior distribution. So it's kind of the intersection of control theory and information theory. And the idea is team decision theory. And so imagine there's something that's continuous value that's my high level goal that I'm trying to achieve. And that's like this number W that lies on the 0-1 interval. And I'm sequentially signaling to the computer, and I'm signaling with this signal X. And this is the signal, for instance, that's in my brain. Either I'm imagining squeezing my left hand or I'm imagining squeezing my right hand. And then Y is just like what we showed before. The Y are the voltages associated with the shower cap that I have on my head recorded with the EEG. And the formulation I wanted to come up with was the computer is giving me some type of feedback, right? And so it's kind of like when you're driving your car that's misaligned, you see the trajectory of the car is steering one way. And so then the subsequent control signal, the X to T that you give, is in some sense a corrective signal to try to help steer it. And so the high level idea that came to my mind is how can I formulate this just for starters, overly simplistic. And oh, and by the way, the computer, what is it sequentially doing? Well, what came to my mind is that ultimately we want the computer to accomplish the high level goal of the human. So let's suppose that the computer is maintaining some probability distribution that reflects its belief over what's happening given everything it's seen so far. So that's what Z time T is. So we can think about this from team decision theory, which is basically optimal control, but now when we have multiple agents, one agent being the human and one being the computer. So imagine I'm trying to optimize something. I'm trying to maximize some accumulation of rewards. And I want to obey the principles of causality, meaning that the next signal that I give at time T is a function of the high level goal that I have, which is W, as well as all the feedback that the computer has given me, which now I'm just representing as all the Y's up until time T minus 1. And then obviously the belief that the computer makes at time T is a function of just the things that it saw, Y's up until time T. So this is actually a team decision problem with non-classical information structure. If people remember things like the Witzenhausen problem or things along these lines, this fits that. And so another thing came to my mind is, okay, so what should the reward function be? What do I want to maximize? Well, ideally what I would like is I would like the computer, I'd like its belief about the message to be as narrow as possible, ideally to converge towards a point mass at the message point. And so one way to think about this is let's make this a maximization of the mutual information. So suppose that Z is a posterior distribution. So if I let the reward function be basically the Rn derivative of the posterior time T relative to T minus 1, then when I accumulate that over time, what I end up with is the mutual information, right? Because if you think about this, in essence, what I'm saying is if I take the sum as T goes from 1 to some capital T of the log, so what I'm saying is basically d pi T by T minus 1 evaluated at W. All this means didactically, suppose that these things had densities, right? Then this is the log of the density of W from the Y's up until time T divided by the density Y's up until time T minus 1, right? Evaluated W, right? Likewise here. Notice what's going to happen is that all what's going to be left ultimately, this is just going to become the posterior all the Y's up until time T divided by the prior. Right. So that's exactly what this becomes because these guys end up in a numerator and a denominator from T going from 2 to time T minus 1. And when you take the expected value, you get the mutual information. Okay, so it should be clear to everyone that the expected value of this quantity is the mutual information. So if I set up my reward function that way, then I end up with the mutual information. So I'm here at UC Berkeley. So I want to give a shout out to Walron and Varaya because when I was looking at this problem, there was this 1983 paper by Walron and Varaya, and to my students. By the way, I've got 4 students here. Stand up. Andrew, Alice, Sabrina, Tomash, right? So 4 students from the other side of the bay. There's just a learning lesson to them. So we're here in Berkeley territory. So these are 2 legendary figures at Berkeley. And they had this really interesting paper in 1983 called Optimal Causal Coding Decoding Problems. And so you have a noisy channel right here. You have an encoder that's taking causal information from all the previous Y's. So here they're assuming that there's a Markov source that's being given to you, but mine is a Markov source because I can just let W is just W, right? But W is Markov because you can index it over time, but it's always the same W. And then you have this receiver right here that's operating in this way. And in our example, these updates, right? These Z's, remember, I want them to be posterior distributions. And so one of the things that they talk about is that there always exists an optimal encoder that operates on just the most recent input of the Markov source and the most recent piece of feedback from the decoder, okay? So this began to be interesting. And so I want to map this back to our problem. And so sort of building upon Walrond and Varia, I can now constrain the class of encoders and decoders to have this type of structure. And the decoder, as I alluded to, it's quite obvious. And it turns out it's kind of cute, but remember for that mutual information objective that I have, what I can show is that there's all this KL divergent stuff that occurs, and the optimal decoding scheme is exactly what you thought it would be. It ends up being just a posterior update, right? So the optimal Z at time t, given everything so far, is literally just Bayes' rule. Okay, so the $64,000 question is, how should the encoder behave? And so it turns out, if we stand back and we think about this, if our objective is to maximize mutual information, and notice that this, I'm assuming that this noisy channel is a memoryless channel, then we know that the mutual information is upper bounded by the capacity. Moreover, we know exactly the if and only if conditions, and the two if and only if conditions are that the next signal to the channel should be the capacity achieving distribution of a one-shot use of the channel, but more importantly, at time t, the next signal should be statistically independent of everything the decoder has seen so far. So this is in standard covariant Thomas when you take the information theory class, when you look at how the capacity is unchanged with feedback. So if we look about an example of a BSC, suppose, as I alluded to before, X is just imagining left or imagining right. And remember, this is sort of what our P of Y given X looks like. And you can, without loss of generality, you can assume that that's a BSC because there's symmetry. So it turns out that Horstein thought about this problem way back in 1963, and then Shayevitz and Fader in 2011. So Horstein came up with the scheme, but he didn't prove that it actually achieved capacity. But this was proved by Shayevitz and Fader in 2011. And in fact, they generalized it to an arbitrary memoryless channel. And so what if we focus on the BSC for a minute, the first thing you do is you take the posterior density, which is pi t minus 1, and you compute its CDF. You see, this is this function evaluated at W, and it's the integral from 0 to W. So this is the CDF of the posterior distribution. And then basically what I do is I take the CDF of the posterior distribution and I evaluate it at W. Okay, so I'm just taking the posterior distribution and evaluating it at the message point. And then all I'm going to do is I'm going to compare that to a threshold of 0.5. And if you're less than 0.5, I signal left. And if you're greater than 0.5, I signal right. Okay. Is that sort of clear to everyone? And what I want you to appreciate why this is achieving, why this is at least maximizing mutual information is because notice what I'm doing is, so you see S at time t minus 1 is the CDF of the posterior distribution. And then I define WT to just shove in W into that object, right? So notice what I'm doing is I'm shoving a random variable into its own CDF. Do you guys remember in your undergraduate probability class that you either teach or you taught that when you shove a random variable into its own CDF, the output is always uniform 0, 1. So irrespective of what the previous Y's were, this is always uniform 0, 1. So notice the right-hand side is not depending upon the Y's up until time t minus 1. So this is always uniform, and moreover, it's statistically independent of all the past Y's. And then literally all I do is I shove it into this object, and all this is doing is this is just shaping. This is shaping to make sure that X is 1/2, which is capacity achieving for the BSC. So this part is easy. This is just a quantizer, right? It's shaping it so that it has the optimal distribution for the one-shot use of the channel. But more importantly, we're making sure that it's statistically independent of everything the decoder has seen so far, right? This is literally undergrad probability stuff, right? So clearly this is maximizing mutual information. In particular, at every time t, this is exactly the capacity times t, the aggregate mutual information. And Shayevitz and Fader also show that this actually also achieves capacity. The posterior is contracting at an exponential rate, right? Where there's a volume of probability approximately 1, that has length 2 to the minus nc. So that's nice. So the question becomes, does this exactly map to the problem with human computer interfaces that I was interested in? And I argue no, because a human cannot accumulate all the past measurements that the decoder has, the channel has seen. As a human, you're going to give the human all the past EEG waveforms and have the human figure out what to do next? Well, no. What should be nice is maybe something that looks like this. And so the idea is that the decoder has all the past Y's. And then what it does is it provides some type of query to the human that is simple as possible, so the human can just maybe perform a very simple comparison, right? So remember, humans, we have limited sensory capabilities, right? So you want to minimize the question that we ask them. So the question becomes, can we sort of map this to this? And notice I put the dashed lines because you see this is everything the y's up until time t-1, which is encoded in this posterior distribution. And so this aggregate box is almost like the encoder with feedback. But part of it is the computer and part of it is the human. And so I can formulate it this way and say, well, let me optimize over all of these functions tau. And I want to have a query point, which perhaps is also a number on the 0-1 line. And so the only thing I'm giving to the human is a number on the 0-1 line. He has his own intended number on the 0-1 line, and maybe he performs a very simple comparison to signal. Can we do that? And it turns out that the answer is yes. And it turns out that there's a 1-to-1 correspondence between the original way, where what's signaling is all the past y's, and a simpler scheme where what I do is if I'm the computer, I have the posterior distribution and I calculate the median of the posterior, which is a simple number on the 0-1 line. And all the human does is they just do a very simple comparison. They basically just do, if the query exceeds the message, then I signal left. And if the query, on the other hand, I signal 1. And this is the dynamics of these are in 1-to-1 correspondence to each other. But hopefully what you can appreciate is this is something more amenable to a human. Well, Letha, you have a question.
So this median came out of some equivalent optimization.
It turns out these are exactly mathematically the same thing. This actually goes back to Horstein in his 1963 paper. He shows this. Yeah. So for this, for the BSC, this is a 1-to-1 correspondence. Because if you think about this, what is the median? The median is the point for which half the posterior probability is to the left and half the posterior probability is to the right. Yeah. So, but you see the key point. I deliberately wanted to engineer something that looks like this because a human, you want to minimize the query information you're giving to the human. So we actually did some fun things with this. So, this is like around 2011, we published a paper, Feedback Information-Theoretic Approach to the Design of Brain-Computer Interfaces. So what we did, you guys know this from your information theory class. Remember in Shannon, in his original paper, he was interested in the statistics of the English language. It's kind of funny because that's the essence of what Chat GPT is, right? Well, it's building a good predictive distribution. Right. So all I'm doing right here is I'm basically doing what Shannon did in his original paper, and I'm building like a Markov model of the English language. So imagine that the message point is a very long sentence that someone is trying to convey, right? And so as you guys know, I can put that as 1-to-1 correspondence with a point on the 0-1 line, where what I do is I make the first sentence. Think about like Shannon Elias coding, right? So the length of this interval corresponds to the probability, right? So you see T takes on a lot of length and Z takes on not that much. And then inside of here, this now is the conditional distribution, given that the first character was T, yada, yada, yada. And so we basically built this. And so as you see, as you go into a longer and longer sentence, that's a longer and longer sequence. So the width is getting smaller and smaller. So ultimately, it's like an infinitesimal point that I have in my head that I'm trying to convey. And so what we're always doing is we're always making this basically the median of the posterior. Before any information, this is literally just the 0.1/2, right? And I'm comparing. And then what I do is I warp the display so that the median is always at 1/2. So I'm zooming in on some areas, so the median is always at 1/2. And as I can, this is an instance of us really signaling across a BSC with our brain-computer interface. And what we're doing is we're warping with the posterior distribution so that this is always 1/2. And you see the effect is that you start to zoom in and you see more and more you're zooming in on T. H has a lot of probability. And over time, you end up spelling the black cat jumped over the lazy dog or whatever the famous sentence is. So another instance of what we did with this back when we were over the cornfields of Illinois, we got interested in actually doing something crazy like trying to specify a smooth path. And we were thinking, imagine if we could fly a remote controlled airplane over the cornfields of Illinois. So the first step we wanted to do is represent that as a sequence of small little arc lengths. You can think about a path as a sequence of arc lengths and assume that there's a finite number of those arc lengths. So again, it's just a sequence of things that are finite in nature. And so I can encode. And actually what we ended up using, I don't know if anyone remembers Tom Culver's paper from the 1970s called enumerative source coding. So we're building upon Culver's enumerative source coding here. And so now what happens is the decoder has a posterior distribution. And so right now it's flat, it's uniform. And so the decoder provides a query. And so that query is some number on the 0-1 line. And so that corresponds to a path. So we have our desired path, which is in green. And then we have the blue path, which is the query. And how we're using Culver's enumerative source coding is that one of the things that he shows is if you have this lexicographic type of structure, then you can maintain kind of orientation and whatnot, right? So we're taking advantage of that. And so all you have to do to compute, because remember, all you have to do is you take a look at the median and you say, are you less than or greater than the median? But now I have a sequence of arc lengths. So how do I do a comparison? Well, covariant enumerative source coding, you can maintain that by looking at the first location where the two sequences differ. And then basically, if it's counterclockwise, that means imagine left. If it's clockwise, it means imagine right. So I sequentially do this. So now the posterior distribution gets updated from the brain waves in my head. And so now it calculates the new median of the posterior distribution, which is this red vertical line. It goes through this lookup table, and this point corresponds to that path right there. So then it shows this blue path on the screen. Keep in mind, the only thing that's on the screen is the blue stuff. The green stuff is in my mind. And I'm looking at the first location where they differ, and I signal if it's clockwise or counterclockwise. And over time, the posterior distribution is beginning to contract. And moreover, my true path, as well as the path that's being shown, are overlapping more and more, and not until latter and latter parts do they disagree. So we actually, did some fun things with like Google Earth and built a BCI paradigm. And so this is an instance of me spelling this with my EEG back when we were in San Diego, and I was on my way to give a talk at Princeton, actually. And so I specified a path from San Diego to Princeton, as you can see here. And we did some other fun things with this, as I alluded to. Our real hope for doing this was to actually fly like a UAV over the cornfields. And so we collaborated with some aerospace engineers, and we were able to do this. And so here's a little video. You can see, you see this is just with the brain waves, and he is just specifying that path. And here's the plane flying, and it's sequentially flying over the cornfields of Illinois. One other thing that's nice about this paradigm is if you notice where the paths differ, it ends up being further and further parts of the path. That gives time for the airplane to have momentum to fly. So there's another kind of extra benefit of the dynamics that just comes out of this. It's just luck, to be honest. So how does this relate to the title of my talk, which is all this generative modeling stuff? I'm just inching you there little by little. So what if I wanted to do a signaling paradigm where it's not the 0-1 interval? So for instance, suppose I want to specify a point on a 2D map or something in higher dimensions. The essence of the problem is exactly this. Right now I have this point that's in my head, that, for instance, it's in R2, and the posterior distribution is going to be a posterior distribution over R2. I still want to constrain the query point that the computer provides. How do I think about this? And what I want you to remember is we cannot do exactly what we did in the 1D, because if you remember, this whole thing about making sure that the next input was independent involved using a CDF, shoving a random variable into its own CDF, right? But a CDF, what's the output of a CDF? It's always a number between 0 and 1. But remember, I'm trying to signal something that's an R2 now. So hopefully you can appreciate that I cannot just use the CDF trick. So I had to rethink about what was even happening in the 1D case. I had to think about it differently in a way that can generalize. Is that clear to everyone? So this is what we did before, but I'm using the CDF trick, right? The output of a CDF is a number between 0 and 1. How can that apply if I'm in R2 or something else, right? So what we had to appreciate, and it took us a long time to appreciate this, that really what we're doing is we're building a map that's transforming a sample from the posterior distribution into a sample from the prior distribution. That is the essence of what we're doing, because if you stand back and you look at this, think about what this map is doing. So remember, I have y's up until time t-1, and with that, I have the posterior distribution, right? But then ultimately what I'm trying to do is I'm trying to generate something. So remember, I want the next input to be independent of everything the decoder has seen so far. So if it's independent of everything the decoder has seen so far, it should just be uniform 0-1. So that means what I'm really doing is I'm taking a sample from the posterior distribution and transforming it into a sample from the prior. So I'm transforming something from P to Q, right? So really what we were doing before was taking the posterior distribution and building a map that's a transformation from there to the prior. And these can be distributions in arbitrary spaces once we realize this. And so that's how we can generalize this to arbitrary dimensions. Is that clear to everyone? The essence of what we were doing before is what is here. So I always remember X is always just some quantizer on that WT, right? To make sure it has optimal capacity achieving input. But the key thing is I want WT to be, you see there's this relationship between WT and the original W, right? And what is the key essence of this map? This map is transforming a sample from the posterior distribution to the prior distribution. That's the essence of what this is doing. So it turns out with that, we can actually generalize this, right? So, I can imagine that it's something about a map transforming a sample from P to Q when I define P and Q appropriately. So once we realize this, as you'll see, we thought about a formulation more generally, the essence of how can I construct a map so that I can transform samples from one distribution P to another Q. This is like the Plinko board example, if anyone is familiar with that, right? The balls drop out and you want to engineer the locations of these little things so that when the force of gravity drops these down, they come into this new shape right here. This is sort of the essence of what we're trying to do. And I argue that we can actually solve many problems with this. In particular, we can solve problems in Bayesian inference, in active learning, as well as generative modeling. The last thing I want to say is I hope you guys can appreciate when I have that, when I do that query point and you're just comparing to a query, does everyone appreciate that this is really an instance of active learning, right? Once we look at it from that query perspective. So in some sense, we can solve many problems with active learning. So here's a statement from Michael Jordan. He said, I think data analysis can deliver inference at certain levels of quality, but we have to be clear about what levels of quality. We have to put error bars around our predictions. And what he means right here is suppose, so this is like before deep learning, like, before deep learning really took off. This is around 2014, where the hottest thing since sliced bread was, using convex optimization algorithms to build MAP estimates, right? And, L1 regularizers and things like this. Can anyone even remember before deep learning what the hottest thing was, right? Compressed sensing and all that. So the essence of what he's saying is suppose that you have two posterior distributions, the green one and the blue one. Notice that the MAP estimate for both of those is the location of that red dot, but the green one has more uncertainty than the blue one. So he's saying it's insufficient to just get, we need to think about the error bars. Now, how do we do this in high dimensions? By the way, this wasn't Michael Jordan, basketball player, Michael Jordan here at UC Berkeley. So shout out to UC Berkeley once again. Okay, so in the spirit of what Michael Jordan said, how can we think about this? How can we think about quantifying the full uncertainty with respect to the posterior distribution? And just as an example, a lot of things that we do with Bayesian reasoning is we want to minimize some loss function with respect to a decision variable, but there's some latent variable from which we have noisy observations of, right? So this whole setup of achieving the Bayes risk and whatnot. And the high level point is that I can approximate this conditional expectation if I could get IID samples from the posterior, right? So the idea here is A is an action, all right? So if I take one action, what is going to be the loss? The loss is with respect to the latent variable, but what I've measured is Y. So in some sense, for optimal decision making, I want to minimize this conditional expectation. Well, if I had IID samples from the posterior, then clearly I can approximate this quite well. So what I hope you can appreciate is in many situations when we do Bayesian reasoning, we can sample from the prior easily. It might be a Gaussian or a Laplacian, something we can sample from easily. When can we build a map that can transform samples from the prior into samples from the posterior, right? And if so, then I can generate IID samples from the posterior. Another instance is active learning. And what I want you to appreciate is all that stuff I talked about with brain computer interfaces and all that, that's really just an instance of active learning, right? Because you guys remember what the canonical example of active learning is? Like I have a number between 1 and 20 in my head, right? And you ask me a question and maybe you hear it through a noisy channel. You need to figure out what's the sequence of questions that you ask. All right, so the number between 1 and 20 is the W. And then the question that we ask is Q. And we know that there's smart sequence of questions you can ask and there are dumb sequence of questions you can ask. It's in essence the same problem. So I hope you can see how this maps active learning. And then the title of my talk, I mentioned generative modeling. And the idea here, and I'll showcase in just a moment, is we think about the essence of what underlies the ideas of a GAN. I have IID samples. I have a bunch of pictures, right? Pictures of cats, pictures of dogs, or whatever it is. And what I would like to do is I would like to build a generative model from which I can generate new pictures from that. So if I take every picture and I take the RGB values, I treat that as a point R3. I have a bunch of pixels. If I have n pixels, then that's point in 3n dimensional space. The idea is that if I can take those IID samples and transform them, for instance, into a standard normal in 3n dimensions, then what I can do is I can generate new samples from a standard normal in 3n dimensions and go through the inverse map. And in principle, I can generate new pictures, right? So hopefully everyone can see that this is an instance of this too. So what I wanted to do was to have like a Swiss Army knife framework where I have one problem formulation that can solve all three of those problems. And so the idea is that suppose that I have n samples that are IID from some distribution P, and I may not know it. And what I want to do is I want to transform them to some distribution Q. And to capture the essence of the Bayesian inference problem, suppose I know the density of Q only up to a normalization constant, because we all know in Bayesian reasoning in high dimensions, a lot of times we can't get the denominator. So suppose I only have the density of Q up to a normalization constant. And a key assumption I'm going to make is that Q is log concave. And the reason I say that is because in many of the instances it is. So for instance, remember in posterior matching, I want to remember P was the posterior distribution, but then Q was the prior. And Q was like uniform across the unit interval or the unit square, right? So that clearly is log concave. If you think within the case of Bayesian inference, when is even just getting an MAP estimate of Bayesian inference a well-behaved problem? Well, it turns out when the posterior is log concave, right? So I hope you can appreciate is that there's, even solving simpler problems, the need for Q to be log concave is natural. And so my objective is to estimate a map S to transform samples from P into samples from Q. And so one way that we can think about this problem is that there's this anchor Q that we're trying to get to, and we know what Q is, or at least we know it up to a normalization constant. We can ask ourselves, suppose I pick an arbitrary map S. What would be the underlying P for which S transformed P to Q? Again, if you guys remember undergrad probability, right? Suppose that S was well-behaved. Suppose, for instance, that it was monotonic, right? Then remember that there's the transformation of variable equation, right? So the density of P at U induced by the map S is Q at S of U, but then the notion of length changed. And this is like S prime of U if we were in one dimension. And more generally, this becomes a determinant of Jacobian in higher dimensions. So one thing I'm doing right here is I'm forcing my map to be the set of maps that are monotonic. Okay, and it turns out with all loss of generality, I can do that. Anyone here who knows a little bit of optimal transport knows that if P and Q have densities, there always exists a map that lies in this space that does that. And this is a famous result by a French guy named Brenier, right? There always exists a map that's a gradient of a strictly convex function. So if it's the gradient of a strictly convex function, then convexity means that the second derivative information is not negative. So that means the Jacobian is positive definite. That basically means it's an increasing map. So we can always do that because of Brenier. Okay, so here's the idea. The idea is that there's this true S star that links P to Q. If I pick an arbitrary S, then this is just the change of variables formula from undergrad probability. So that's going to be some P toolty that's induced by that S that's over there. So since Q is anchored, maybe what I can do is vary across all S's, and I'm implicitly varying across all these P toolties and wait until P toolty is close to P. So if you think about that for a moment, that's kind of the essence of maximum likelihood estimation. And what I mean by that is that when you think about maximum likelihood estimation, I have IID samples X, and they're drawn from a class of densities that's parameterized by a theta. Remember what I just did previously is I had a class of densities that are parameterized by this map S. Okay, and as I search over all of these, or I pick the one that maximizes the log likelihood, that's the same thing as minimizing the negative log likelihood. Keep in mind, these are the IID samples from P, right? So this is the empirical expectation, which is approximately the same thing as a true expected value. I can add or subtract anything that doesn't vary with theta. So in particular, I can put the log of the prior in there. So really what I'm doing is a KL divergence minimization, right? So as we all know, this is the essence of ML estimation, right? The essence of maximum likelihood estimation is minimizing the relative entropy between the true P and the P toolties parameterized by your theta. So, one way I could think about this problem is doing that, right? So I could try to do some ML estimation over the space of monotonic maps, right? So all I'm doing is I'm just rewriting what we did for maximum likelihood estimation. And now going from here to here, I'm just using our change of variables formula. Remember, P toolty evaluate any U is Q of S of U, right? And then multiplied by the determinant of the Jacobian. So now when I take the negative log, I get this right here. And now here's where I hope you can start to appreciate why I wanted the function to be log concave. So remember that Brenier told us that we can always let the map S be the gradient of a strictly convex function, which means the Jacobian is positive definite. Do you guys remember from your convex optimization class that the log det operator is always concave over the space of positive definite matrices? So this object right here is always going to be, if this is concave, then it's negative, right? It's convex. So this object is always convex in the space of the S's. And if Q is log concave, that means the negative log of Q at S of X is going to be convex. So at least, this is a convex problem. So this is how we first started thinking about the problem. But if you think about the class of maps, if P is not close to Q, then S necessarily is going to be a very nonlinear map. So although this is a well-behaved convex problem, we start to play around with this. But if I wanted to come up with some type of basis to transform these maps, it's a very nonlinear map. Okay, it's convex in the space of, in the space, but how am I really going to search through this? We're not sure. So we started to play around in the optimal transport world. And it turns out that there's another way that you can build a sequence of maps that transforms something from one distribution to another. And this is basically Langevin dynamics. And so the high level idea is if I, suppose that I have a system that's not in thermodynamic equilibrium. When it's in equilibrium, we know that the distribution corresponds to the Boltzmann distribution. So let's imagine that corresponds to Q. That's when it's in equilibrium. It's the Boltzmann distribution, that's Q. I can always take Q and represent it as a Boltzmann, right? Without loss of generality, I can do that, right? Okay. But remember, we started off with IID samples from P. So let's almost imagine like it's out of equilibrium. And now I want to watch what happens when it starts to go back to equilibrium. Well, people know that obeys the Langevin dynamics, right? It's a stochastic differential equation that sort of describes what occurs. And here's a sort of discretization of it. So at initial time 0, it's at time P, and it's basically converging. And keep in mind that this nabla on phi is the energy function inside of the Boltzmann distribution. So this is a stochastic differential equation, a discretized time. What's cool is that, so this is the continuous time sort of version of what's happening. This is the SDE of it. There's a one-to-one correspondence between, so remember, this is like a generative statement about if the sample times 0 came from P and it eventually is going to converge to equilibrium. Equivalently, you could think about the distribution of the samples, right, and how they're evolving, and they're evolving according to a PDE known as the Fokker-Planck equation. You guys don't need to know the details of it, but there's a one-to-one correspondence. So all the high-level conceptual thing I'm trying to do is I want Q, my anchor, where I want you to end up. I'm going to represent that as a Boltzmann distribution. The sample started off at some P, right? And I'm going to just let the laws of physics bring them back into equilibrium according to this equation. And what's nice is that it's a continuous evolution. And so what that means is underneath this, the distribution at time 0 was P, and it's little by little moving, and it's moving towards Q. And if you discretize time, then clearly it's a very small infinitesimal change, which means that the underlying map going from P, say 0 to P1 when I discretize time to P2, each of those are infinitesimal changes. They're almost identity mappings. They're slightly nonlinear mappings close to the identity. So maybe I can parameterize these better. And so something else that was cool that I stumbled upon is this famous paper. They call it JKO because the first character and the last names of the authors are JK and O. And so this is a famous paper in the field of optimal transport theory, variational formulation of the Fokker-Planck equation. And basically what they show is that evolution of the densities obeys, you can look at it differently. And the way you can think about it is that I define the Wasserstein distance, which I hope many of us know what it is. It's a optimal transport distance between distributions. And the high level idea is that when the density is at some time point K, and it's evolving, it's going to go, then it's going to go to time K plus 1. We know that it's kind of going towards the Boltzmann distribution. It's moving towards Q. In what sense can we mean that? Well, what we mean by this is that, so rho infinity is Q. Okay, so rho infinity is Q. And so what I want you to do is I want you to make the relative entropy between where you are or your next step in Q to be smaller, but I don't want you to be too far away from where you were previously. And so this is, and then the limit as h tends to 0, this is exactly the dynamics of this, right? And actually the way this is written is that this is a gradient descent of the relative entropy with respect to the Wasserstein distance. And do people remember why this in some sense might be a gradient descent? If I have time, I can draw it on the board. But so when people think about, I'll just give you a hint right here. It's something called implicit gradient descent. So when you, hope people over there can see. When you do gradient descent, the way you're typically thought about it is I always forget the minus and the plus, right? So if I'm trying to minimize this function, right? And I'm right here, and I know that this is the minimum. So I say that x at time t plus 1 is going to be equal to xt, right? And so notice if I'm at this point right here, then I want to go to the left, right? But notice that the derivative of the function is positive, so it ends up being minus, right? Some gamma times f prime evaluated at xt. Is everyone familiar with that? This is an implicit scheme. Oh, sorry, this is an explicit scheme. You can build an explicit scheme where you say xt plus 1 equals xt plus gamma f prime at time xt plus 1. Put xt plus 1 right here, and then you implicitly solve for xt plus 1. And it turns out that, and I can go to this later, it's a bunch of math. What you can show is that this is, you end up having just the Euclidean distance right here, and this right here is just the function that you're minimizing. It ends up being exactly that. Okay, so yeah, and so this becomes the Fokker-Planck equation. So something else that's nice is that when Q is log concave, and remember I want that. If Q is log concave, it has a little extra property that it's a little more than log concave. If it's a uniform log concave, which basically means that when you look at the you know, the second derivative information is basically strictly greater than 0 as compared to greater than or equal to 0, and the generalization of that in higher dimensions, which means that the do you guys remember what this means, right? This means if I take the Hessian and I subtract off lambda I, then that's a positive definite quantity. That's all that means. So if that holds, that you get exponential convergence in time. So what this means is if I build very small little discretizations H, then I know that the Kehl divergence is converging exponentially fast. And this is another famous result in optimal transport theory. So what I want to see is if I do math on this, does anything cool happen? And it turns out, luckily, it does. So remember, this is basically the variational formulation of the Fokker-Planck equation by JKO. But remember, I don't care about the distributions. I care about the underlying maps. And so is there something I can say about the maps? And it's not too hard to see, but now suppose I build an objective function over maps where I have rho at time k minus 1. This is the induced map by that S. Remember that update equation right here? And this is basically where you would be at the next time step. Notice, by the way, that these two things are in some sense reversed, but because the KL divergence is invariant to invertible transformations, this and this are the exact same thing. And when I minimize over all possible maps that are monotonic, I'm basically going to get this quantity. So it turns out this minimization problem, that minimization problem are in essence the same thing, but here I'm representing it over maps. Okay, so now what I wanted to do is I want to look at this problem over maps and think now, remember all I have is IID samples, right? I actually don't have the distribution P. But the beauty is I can just, replace this with taking IID samples from this. So just to remind ourselves, this is what we had from the previous side. And now what I'm doing is, remember that P2, I'm representing as Q of S of X times log that, times the det. And then I take the negative log. And then I still have this remaining term right here, which is just X minus S of X squared. And now the only thing I'm going to do is I'm just going to replace this with the empirical expectation with respect to IID samples. And the beauty is that when Q is log concave, I always get convexity here because you see I have negative log of Q. Remember, log det is always well behaved. And this is just quadratic in S, right? So I get log concavity here. But what's also nice about this is that now I can parameterize these maps like with a basis or something with a bunch of functions that maybe are almost the identity with slight nonlinearities, because remember I'm discretizing very, very slowly. So each remember rho k minus 1 and rho k for small discretizations are very close to each other, which means that the map is almost the identity map with slight nonlinearities. So I do that. And then, so one way I do this is something called the polynomial chaos. And the reason that we do this, so you see you have the identity operator, plus you have some of your nonlinear terms. And at a high level, what I can do is all the polynomial chaos is a set of maps that are basically orthogonal with respect to some distribution, right? And so if I have information about the distribution that I'm trying to get to, I can get there. So I had convexity, but something else that's nice, for instance, when you use the polynomial chaos, is that log concavity of Q implies sub-exponential tails, which means that these are dense in L2 of P, which basically means as you use more and more of these, you actually are representing, it's quite obvious what that means, right? That and the limit is I use more and more maps, I can actually get the true optimal map. So then the next step is just some details for you guys, but since part of this is about privacy and security, I thought you guys might like this because Vince Poor has written papers on solving ADMM problems and maintaining differential privacy. We didn't do this, but I think there's an opportunity to do this. That if you stand back and you look at this problem, I have these ID samples with these XIs, but I have a common map S that I'm searching over. So in some sense, looks like a problem like this, right? And if people know anything about ADMM, this begins to fit the framework of ADMM. And the essence of the ADMM problem is something like this, where I have f of x plus g of e subject to the constraint that ax plus bz equals c. So if you remember, what we can do is we can build a penalized Lagrangian, where we have our original Lagrangian, but we add this quadratic term right here. And what this allows us to do, this allows us to do coordinate descent and guarantee that we'll get the optimal solution. So if anyone has played around with ADMM, there's this saying, all men are created equal, but not really. There's all these weird things that you might have to do where you have to introduce an auxiliary variable really carefully and yada, yada, yada. So we introduce some auxiliary variables. Each of these WIs have to be this common consensus variable B. And we introduce these other variables associated with the Jacobians and other things. And when we do this, we get, this is what our penalized Lagrangian looks like. And what's very nice about this is that all three of these terms now are quadratic and they have closed form solution updates. And some of these you only need to solve once with linear algebra. And once you solve it once, you never have to do it again. So using this, all men are created equal, but not really analogy, when we parameterize the maps this way, the set of updates for ADMM are basically every single one is a closed form linear algebra update, except for one, and this one is a point estimation problem, almost like solving an MAP estimation problem in just D dimensions, right? So it's just, you see, you have negative log Q, right, plus a quadratic penalty. So it's just like solving some type of MAP estimation problem. And what you end up doing is you end up solving each of these across separate nodes, and then you do your consensus updates. And we actually implemented all this in AWS. And remember, this is, it's like 2010, something around there. Oh, no, sorry, 2017, something around there, we were doing this. And so what's really cool is that each one of these nodes is just doing a linear algebra update, solving one D-dimensional convex optimization problem, integrate everything together, and you can do this. And
But you're building a brain interface, and you don't have to do it on a chip.
Well, I was thinking the more general problem. So even generative modeling is almost like the GAN problem, but something where we can guarantee, theoretical properties about how it behaves. What's also nice about this is when you use GPUs, you get performance improvements, right, with the number of dimensions. So yeah. So remember the number of dimensions that we're in? This is the beauty. So yeah, and this is the statement about all men are created equal, but not really. When we formulate the ADMM problem this way, all of these are linear algebra updates, matrix inverses, and one D-dimensional convex optimization problem.
I mean, it's very similar to a Prox map.
Yeah, that is really proximate.
Because there's that there are various works on debiasing the discrete time JKO, because discrete time JKO is biased. It does not have the right invariant distribution. But using Prox and splitting methods, you can actually come up with various ways of doing it.
So I wasn't aware of that. So you're saying, well, that might be implicitly what we're doing, because this is, the proximal operators underneath all this, because we're using ADMM, right? So,
yeah, I mean, this is very, very just recent works about, that's like Colt, last year.
I'm not aware of that. So that's why it's good to have Max here, students. Remember I told you guys, he's a walking encyclopedia. So so the results from the simulation. So what we end up doing is, so the high level idea is now we're composing a bunch of maps. So this is kind of like a deep network in some sense. We're composing a bunch of nonlinear maps, but how we're building each one is different. We're using convex optimization. So when I compose all of these together, I'm basically doing that Langevin dynamics or equivalently Fokker-Planck equation. So suppose I start off in 2 dimensions and I have a, I hope this thing is going to run. It's supposed to be animating right now. Sorry, let's see if it will. I don't know why it's not. Oh, there it is. Is it going now? Yeah, so it starts off as like this bimodal, almost like a mixture of Gaussians. And remember, all I have are IID samples. One beautiful thing about this result is I don't need to know anything about the distribution on P, as long as they're IID. Because remember, I want to capture the GAN problem where I just have these images, right? I want to generate new images. And the only thing I'm saying is I want to sequentially build a composition of maps so that when I compose them together, the aggregate is going towards a standard normal Gaussian, as you can kind of see there. And I think you can see the points, and they start off as kind of bimodal. And these are the transformations of the points. And you see that they're being transformed into a Gaussian block. So some results with this framework. In terms of Bayesian inference, we were able to address that problem. So here are IID samples from the prior, and we transform them to ample IID samples from the posterior. This is like a 95%, window with respect to the prior, and this is the 95% credibility interval. If people are familiar with that, it's basically the equivalent of the confidence interval when you're doing Bayesian inference. We carefully engineered a scenario where the MAP estimate for the green and the blue were the same, paying homage to Michael Jordan here. And so this is the high level idea is that when you have a small number of samples, you have this right here. Here's where you have a lot of samples. And so here's what your credibility interval looks like. And here's what it looks like here. And notice that the MAP estimate for both is the exact same. So in some sense, what I'm able to do now is I'm trying to go back to that 2014 statement of Michael Jordan. And now we have our quote unquote error bars, right? We have our 95% credibility interval. One thing that's cool, by the way, is with this, if you have the 95% interval with respect to the prior, all you do is you take every point there and you apply the map to it and you get your 95% credibility interval, which is cool. We also showed that basically you can attain the Bayes risk, and we compared our approach to using a Markov chain Monte Carlo approach, and you see that we're achieving the Bayes risk faster, right? So it's not surprising because they're IID samples. In terms of this active learning setup, I won't sort of bore you with this, but this was the brain-computer interface stuff I was interested in. So does everyone remember this picture of Shannon, right? So imagine now I have, rather than a binary symmetric channel, I have like a 4-input channel where and it's symmetric as well. We can just simulate what occurs right here, and what ends up happening is you end up zooming in. So this is the point of interest, is where that arrow is, and you're zooming in on areas that have higher probability, and you sequentially signal. That's what it looks like with respect to that spelling. But we also wanted to do something like specifying a point on a 2D map. So we did something kind of cool where we assume, now suppose that I have two people with common knowledge. And so imagine there's two people and they're distributed in two different parts of the world. Imagine it's like, I don't know, like a crime scene or something, right? And they both witnessed that crime scene, but they're now in two different locations. So they both have this common piece of knowledge in their head. Can I show different questions to both of them and eventually zoom in on this? This is the high level idea. And so we basically were able to use all that stuff with the optimal transport stuff and the Walron Varia, and we're able to engineer interfaces for both of the people. So we actually did this in collaboration with people at University of Puerto Rico. So one of my trainees in San Diego and the other one is in Puerto Rico. And the high level idea is if you want to signal to a 4-input scheme, is it clear to everyone that one person can signal, are you to the left or the right of this line? And the other one signals if you're to the left or right of the other going line, one going from the northwest to the southeast, and the other one going from the southwest to the northeast. So one person is shown one of these lines, the other one is shown the other, and aggregately when they cooperate, they can do it. So literally, this guy's in San Diego, this guy's in Puerto Rico, and they end up sequentially. What ends up happening is the query point is changing. So it's an instance of active learning. And as they're signaling over time, the query point is changing, and you basically are telling me what location it's in. And I can kind of show you how the posterior probabilities are changing. So up front, the posterior with no information is just uniform. After a couple of points of signaling, it looks like this. It looks like this. And so you can see the posterior is contracting, right? It's becoming more and more narrow. Yes, sir.
So just wondering, so this is the analogy of where we were taking a posterior median before. How are you constructing these now? Is it like?
Yes, I can. Yeah, there's in our paper, Proceedings of IEEE 2017, we talk about that. But an interesting question. Yeah, so when we have like a 4-input channel or a finite input channel, there's an analogy to that. But the question of how you do that more generally with respect to this query point, we don't know if that's been fully solved. But for the 4-input scheme, we were able to do it. So that's something that still, I'm not sure is fully solved. It's an interesting mathematical question. So one high level point I want to make here is that this famous quote by David Blackwell that I like, shout out UC Berkeley, you guys see the theme, right? Is, I'm not interested in doing research. I never have been. I'm interested in understanding, which is quite different. Often to understand something, you have to work it out yourself because no one has done it. And the key point is that we originally were really interested in solving this brain-computer interface problem with feedback. In one dimension, we're able to leverage Horstein and Shavitz and Fader, but going to higher dimensions, you can't just use that CDF trick. So we had to really kind of take one step back and rethink what was going on in one dimension and then map it to more dimensions. And that's how we ended up with the optimal transport. And then we realized, well, wait a minute, if we can do this, we can solve a lot of problems. So then we got into the Bayesian inference and the generative modeling. So it all started with kind of, in some sense, this quote by David Blackwell. So then lastly, for generative modeling, this was the title of my talk. So remember, for generative modeling, suppose I have IID samples from this distribution P, and this might be like images or whatever the hell this is, and the structure of this is really awkward and bizarre. If I can transform these samples into samples from a well-behaved distribution like a Gaussian, yeah, so if I can take a map S that transforms the distribution of the data into a standard Gaussian, then what I can do is I can generate new samples from Q and shove them through the inverse map, and now I have new IID samples from P. And that's the essence of generative modeling. One thing that's nice about optimal transport, by the way, is you might ask, does S inverse always exist? The answer is yes. Brenier, there always exists a map, right? That is that's monotonic. And if it's monotonic, then clearly it has an inverse, right? So another benefit that we get is we get the inverse map for free using this Brenier optimal transport viewpoint. So one thing we're able to do is, everyone knows the MNIST problem, right? So 784 dimensions. And so these were the IID samples, and then we generated new samples here. You can see that kind of reflect that. And I'm not trying to directly compete with deep learning algorithms. I'm sure that GAN can do it better, especially with all of the new advances. But the one thing that I think is interesting is conceptually, we can at least prove things about what's happening. It's a sequence of steps, each of which is convex, and it's building upon the framework of some of this optimal transport stuff. And so just, yeah, going to your question about the dimensional Lalitha, that's polynomial in D, linear in the number of samples. What's nice also, remember, is backwards compatible with point estimation methods, because remember, there's all this stuff about building distributed, point estimation schemes. So it's backwards compatible with all that. And what's also nice is it, sort of builds this connection with computational fluid mechanics and longitudinal methods for non-equilibrium thermodynamics, and then obviously convex optimization. So yeah, this is some fun stuff that we were doing, and be respectful of the time. It's 9:58. Maybe we can take a question or two, but yeah.
Lots of questions.
Sure.
So, yes, great talk. I think what you're doing with the generative modeling is very similar to diffusion models.
Absolutely.
Right.
Absolutely.
And I think diffusion models have actually now are outperforming GANs. And so I'm wondering basically whether they're useful to draw from here and actually improve diffusion.
Yeah, so we published this paper in 2019. We were starting to see some of those diffusion papers and whatnot, and we referenced some of them in our work. So we think there's a very close connection. So the diffusion stuff is also building upon Fokker-Planck equation type of stuff. And the key thing that we did, those remember, is we built the JKO variational interpretation of the Fokker-Planck so that we can leverage convexity when we get log concavity of Q. And I wouldn't be surprised if other people are doing similar things. One thing that's tricky is that this is like a red ocean, blue ocean. Cutthroat competition existing industries tends to ocean blade, right? It's like all the deep learning stuff, right? I like to play in this other space, right? So one of the things that I noticed is that after we published our work, other people were doing related work, but they were not citing us. But what can you do? So I think there might be some overlap, but I don't care. I think this was fun. This was cool. Published a paper and graduated my students. So I don't care. But without question, I've seen a lot of diffusion stuff happen.
The related comment, I think there's his regularization by that KL term. Wasn't done in the original diffusion models. And then this is where the noises cannot be tuned as well sometimes. But you see in DALI.
Yeah, I think there are like multiple formulations. Okay. And I think the recent ones are actually similar.
So they might, yeah, because JKO is so popular now. I've seen it in the deep learning community.
So there's a fairly definitive paper from Eric Van den Eyden at NYU called Stochastic Interpolance. And basically it just gives you a unifying view of all these things as stochastic control in the space of measures, controllability. And by the way, so Roger Brockett passed away recently. Yeah. He may have had one of the first papers on this when he had a paper called Optimal Control of the Liouville Equation.
Interesting. So let's nerd out over this on break.
Yes.
Yeah. Well, it's wonderful to see everybody. For the people who showed up late, Aaron, show you my first line. Don't blue, by the way, Aaron. My first line.
Your best work, right?
Yeah, best work. So I haven't seen you in a while, Aaron. So the family has grown. So we got a 6-year-old boy and a 20-month-old girl. It should pop up in just a moment. That's the most important result. Yeah. So, oh, it's not. Let me see if I can do this. All right. So yeah. So with that, let's go to break and let's talk more. Thank you.
So